Well, hello. My name is Paul Irish, and I wanted to share some things with you about performance, specifically HTML5, CSS3, DOM type stuff about performance. Things happening in the front end, the browser, things that could be slow and could be faster. And so we're going to talk about these kind of things. First, we're going to talk about reflows, hardware accelerated CSS, animation, web workers, benchmarking, and a little bit about build scripts. Sound good? Great. Okay, reflows. Reflows. Let's just look at this diagram. This is a diagram put together by Stoyan Stefanov. Reflows, when we're talking about reflows, we're talking about the render tree. That's the really important part. And the render tree is made from, well, it comes from two different things. So we have the DOM tree. The DOM tree is the result after you tokenize and parse your HTML markup. It gets parsed into the DOM, and that's what you see, in Chrome Developer Tools or Firebug, all the elements, right? Of course. At the same time, we have styles coming in, and so we have styles coming in from the style sheets and so on. And when the two combine, we get the render tree. And the difference between the DOM tree and the render tree is that the render tree we have. Let's say that we have an element that is display none, not present in the render tree. So it's in the DOM tree, but it's not in the render tree because we don't see it. It's just not even there. Or if we, manipulate the window size or change the font size, the full page zoom, that of course changes the render tree most of the time, whereas the DOM probably is staying the exact same. So the render tree is what you see, and the DOM is underneath it. A reflow is a change that necessitates a recalculation of the render tree, and it might recalculate, just the very bottom of it, but it might recalculate the entire thing. And reflows can be cheap, but at the same time they can be expensive. Specifically on mobile devices or old IE, they can be quite expensive, and you don't want to do a reflow if you don't have to. And there's ways to avoid them. So first, well, let me show you this. This right here. Oh, this is so cool. This is a debug version of Firefox, I believe. And it's actually laying out the Mozilla.org homepage, calculating the layout and the position of absolutely everything. Oh, this is awesome. And figuring out where it all goes. And then once it's all done and the browser's figured out it, there we go. Pretty cool. But let me show you this one part in here. It's right about, here. Finish off the footer, and then all of a sudden something happens. And then it has to recalculate the whole thing all over again. And I don't know why that happened, but it didn't need to. And we were basically done at this point. And now we have to wait another 30% of our time so that it can recalculate the layout of absolutely everything, when it should have been done. And so this is the kind of thing that we want to avoid. We don't want to have a full page reflow that invalidates the entire render tree. We want to get that finalized render tree out to the user as fast as possible, so that they can interact with your DOM. So what causes reflows? A lot of people have wondered, and a lot of people have thought, checking the element.offset width is normally the trick. But Tony G on the Chrome team dug into this and tried to answer it. So Tony dug in, just opened up Google Code Search and looked for update layout, ignore pending style sheets, and this is essentially what does a reflow in WebKit, and found all these items and then just listed them out. So what we get is this. These are all the properties and methods that will cause a reflow. And so the offset width, which is kind of the one that most people know, is certainly here. But there's a lot of other ones. Interestingly, inner text appears to cause a reflow, whereas inner HTML does not. I'm not exactly sure about that. Scroll to on the window does. So these are all the things that by calling you would trigger a reflow. But what are the kind of typical operations that would do it? Of course, manipulating the DOM tree is definitely going to cause a reflow. Yeah, definitely. If you hide a DOM node with display none, that will manipulate the render tree. It'll cause a reflow. But then any changes to that element once it's display none won't. Whereas over with visibility hidden, if you just take an element, visibility hidden it, there's no recalculation of the page. The geometry of the page stays the same. So actually there's no reflow. We just repaint that one little box and keep going. If we're animating anything across the page, of course we're doing reflows. Depends on, maybe you could overflow hidden it, a container, so that it's kind of encapsulated a little bit. Adding new styles, and then any sort of user interaction like resizing the window, changes the font size, even scrolling causes reflows. So here's a little example about a small optimization that you could do to avoid causing excess reflows. So what we're doing, this is just some simple little jQuery code, right? We are grabbing an element and we're just grabbing the left style property off of it. And then we're going to take that left and apply it to something else. And then we have to do that to another one as well. So we're going to get it here, set it, get it here, and set it. The problem here is that actually checking our style property is going to trigger a recalculation of the styles in a reflow. And because we set something here, it has to do it all over again. So a way to avoid this is we can just bunch our gets together and then our sets together. I'll show you. This is kind of what it looks like over in the Chrome DevTools timeline view. So here we are. We have recalculate style and layout, and these kind of go together. Recalculate style is essentially the prerequisite for a reflow. In WebKit and in other browsers, a reflow is called a layout. Mozilla uses the term reflow. It's just terminology, really. But you'll see here is that in that first example, we kind of do this thing twice before we're able to paint out what the changes are. Whereas in the second one, when we bunch them together, we can get away with just doing a single reflow before we're all set. And then we can paint it out. And I will point out the scale looks a little weird here, but we finished the second time at about 3 milliseconds, whereas the first time we finish maybe about 4 to 4.5 milliseconds. So the third one, in addition to having less reflows, is actually indeed faster. So there's a few strategies for avoiding reflows. The first is batching your DOM changes together, like we just did. Other ways we can do it is you can clone the existing element, work off DOM with that element, and then because any manipulations while it's off DOM are not going to cause a reflow. And then once you're done manipulating it, you can replace that one that was already there and chuck the new one in. If you hide anything with display none, it'll cause a reflow. But if you then manipulate it, all those manipulations while it's display none will not cause reflows, except in IE. Anyways, however, you can take an element, instead of doing display none, you could just take it off DOM, hold it in a document fragment, do your manipulations in the document fragment, and then put it back in when you're done. You only get the reflow when you are manipulating the actual DOM, and when things are off DOM, you're fine. So that one you're fine in IE and everywhere else. Cool. Okay. There's a few more resources I would like you to just check out if you're into this stuff. Slovene Stefanov has done a lot of research on reflows and repaints, and so he's got some great stuff here. BrowserScope has a few tests to see like what triggers reflows. There's a lot of like we were just seeing. There's a lot of small details that are different across browsers. David Barron had a really great Google Tech Talk about browser internals, and specifically aiming that talk at web developers. And so this is, I think, an hour-long talk that you should check out. And WebKit, about like 5 years ago, did a 5-part series on how rendering works. And it's so cool. It's from 5 years ago, but it's totally relevant today. Definitely recommend checking that out. Okay, I think we're done with Reflow. Let's move on. Hardware accelerated CSS. Yeah. All right, getting into some sexy here. So we're just gonna skip right into the demo. This is Isotope by David DeSandro. Let's see. I'm gonna change the sort a little bit, and then I'm gonna insert some new elements. Click around here. Yeah, like this. This is good. Even resize the window, and that responds really nicely. So what's actually happening here is that we're actually using CSS transitions and CSS transforms to do these changes. Now, normally you might think like you're going to manipulate the position of where things go, and you'll probably be like, oh, it'll be absolutely positioned, and then I'll just manipulate left and top and like tell it where it's going to go now. The trick here is that we're actually using 2D transforms translate. So we're using WebKit transform translate, and then we're just changing the X and Y of translate. Now, then we're also using a CSS transition. And as a result, we're able to get all of these operations hardware accelerated, which means, super high frame rates, really high fidelity animations, and they look basically as good as they can. You're writing it in a declarative way so that the browser can be like, oh yeah, I got this. Let me take this. I'm going to take this down to my friend the GPU and optimize this for you. And so it's going to look really good. The cool thing here in Isotope is that David wrote it in a way that it can detect support for transforms and transitions. And if there's not support, then it'll go back to like a jQuery-based animation style. So if your browser is new and good, we're going to do the right thing. And if it's a bit older, it'll still look okay, but not as high fidelity as possible. So this is kind of the power of animations of hardware accelerated CSS. Now, those were 2D transforms, and I was just everything was just moving around on a 2D plane. And normally 2D transforms and operations on the 2D plane don't get hardware accelerated by browsers, and by WebKit specifically. But there's a trick, and there's a trick to make the browser do it. Let me show this clip from Remy Sharp.
Okay, what I'm about to show you is a CSS animation, and it's engaged using JavaScript and just the normal kind of touch gestures. But the first effect I'm going to show you now is one without a 3D transform. So this is just doing a scale and nothing else. And you see it's just a little bit jumpy. That's the actual animation jumping. Now if I show you the same version but just with the translate 3D set on the element that I'm zooming, you can see it's completely smooth. And all I've done is said the image element that I'm pinching and zooming on, I just added a CSS property to say translate 3D.
Yeah, so that's it. I mean, it's kind of a total hack. You can use either WebKit transform translate Z and pass it 0, or do translate 3D. Depending on your use case, one will probably make more sense for you. And all of a sudden, the browser's like, oh, cool, let's throw this on the GPU. And as a result, we can get a much higher fidelity manipulation on the 2D plane, just like we saw in this video. It's pretty cool. There's a few really good ways when you're working with this kind of stuff, to debug it a little bit better. Over in Safari, there's a development flag to turn on some colors. This actually stands for core animation. I'm going to load this up over in the iPhone simulator. And I'm actually going to load this page. This is a tutorial on HTML5 rocks by Malta Ubel. And we're going to show this little demo here. And what we're actually doing is we're detecting support for CSS transitions and transforms. And if we have support, we're just going to use a transform along with a transition. Otherwise, we use jQuery animate. But so here in Chrome, we're using a transition transform. And you see that moves across the screen. I'm going to show this in the iPhone simulator. You can see, the OS is accelerated. Let's scroll down. Here we go. So I'm just going to click, and you'll see, yeah. So And the trick here is that we actually use that that translate z0. We call it the silver bullet here trick to make that hardware acceleration happen. Over in Chrome, we have a somewhat similar thing. Over in About Flags, we have this setting. And let me bring this up. In About Flags, there's a bunch of really crazy stuff. I recommend you dig into this sometime. We have composited render layer borders. And, well, let me just show you what it does. Here's this presentation that we've been looking at, but with this setting turned on. And you can see we get borders around of all the layers that are composited. Pretty cool. So this helps a lot to just verify that, yes, this actually is being composited on the GPU. And then also, you know, in this case, in this 3D case, we have a nice little debug view of what's going on. I will point out that this used to happen as a command line flag. So it didn't used to be nice and handy in this About Flags, but you used to have to run the Chrome executable within a command line flag. And this page over on Peter Beverley's site maintains a list of all the active command line switches or flags. And so I recommend you checking this out. One of the ones in here is show paint rects. And so this actually draws little borders whenever a section of the DOM gets repainted. Why that's interesting is because you want to know, kind of when we were talking about reflows, you want to know exactly how much of the DOM is being invalidated, or the render tree is being invalidated when there's a change. And so with show paint recs, you can see that when you make a change, only the part that needs to be recalculated and repainted is being changed, rather than a much larger chunk, which would be kind of unexpected. So show paint recs is another very helpful flag to use when you're debugging some of this advanced rendering stuff. Over this tutorial has a number of other recommendations around graphics optimizations that you can make, and also digs into JavaScript profiling. So dig into that a little bit more if you're looking to eke out some better performance of your HTML5 app, and these recommendations are not good enough for you. But next, we're going to dig into RequestAnimationFrame. So RequestAnimationFrame basically came about because browsers were like, hey, you know, we know that you're doing animation in the browser, and we know that you're just abusing set timeout and set interval loops to do it. And that's not cool. It's not really cool. Because you know what? A browser can optimize animation better than you writing a set interval loop, just trying to peg the CPU as fast as it'll go. Browser is smarter. So one of the things that it can do is it can batch things into a single reflow and repaint cycle. So let's say that you had a JavaScript-based animation. You're updating like you had an absolutely position element, and you're updating the left and top or something like that. You can actually, the browser can now synchronize that along with a concurrently running CSS transition, or you had some like SVG smile animation running at the same time. It can kind of make sure that those are all going at the same time. It's going to optimize it for 60 frames per second, which is it's the refresh rate of most displays. And so you're going to get the best frame rate possible. 60 hertz is kind of the perfect target for everything that you want going on in the browser. And the really cool thing is that you're really friendly to your users' batteries. Because what happens is that if the tab is not visible, it gets skipped. So let me load this up right here. This is a whoa. Yeah, okay, here we go. So we got this WebGL demo, and you see here we got a lot of action over on the GPU, and this is the JavaScript running inside this page. It's pretty heavy. Gonna move this around. Now I'm just gonna switch to another tab. You see that instantly drop. Oh yeah, yeah. because RequestAnimationFrame is being used, the browser's like, hey, you're not even viewing this tab. We don't need to be wasting the browser, the CPU, the GPU in order to make this happen, because we know that they're not looking at it. Whereas this is, if this field demo had been using a timer loop, it'd still be going. It'd still be eating down my battery here. So I bring that back up, and yeah, plenty our use of the CPU returns. So if you're doing any sort of animation, use this if you can. This actually just landed in jQuery. So this is going to be in jQuery 1.6, and it's also in Gwt, and it's in a few other libraries at this point. So definitely recommend. This is available in both Chrome and also in Firefox, Firefox 4. Over on my blog, we have a nice little shim layer to handle this. We basically feature detect to see if the native support is present, and if not, we're going to use a set timeout loop that optimizes for 60 frames per second, and that's how you use it. Cool. Web workers. The idea here, and I don't want to cover this too much, the idea with web workers that you're probably familiar with is we want to move heavy computation, expensive tasks outside of the UI thread. Pretty much all JavaScript runs in the UI thread, and if something has taken a long time, the user can't interact with the page becomes non-responsive, and in the case of Chrome, we get a sad, freezing, cold tab. He's so cold, and we don't want that. No, that's bad. I want to avoid that, and without web workers, we can. Now, I'm going to show this. This is a little bit more advanced use of web worker, but I think it's really cool. First, normally the way that you instantiate a brand new web worker is you'll be like, new worker, myworker.js. There. Sorry, this is where the code is going now. You pass it a file name, and then it goes and gets that file, and then it uses that file, and that's your worker. Which has its limitations. This here is an example of creating a worker on the fly, basically. So here we have our worker code, and it's a script of type worker. So this is going to get skipped by the browser. So we're just kind of using it to hold some text right now. And then down here in our script, we're going to use the file API, and we're going to use blob builder. Create a new blob builder. Then we're going to grab the text of this script node, throw that into the blob. And then when we create our worker, we're going to use url.createObjectURL with the blob and chuck that in. Essentially, we create a file on the fly and instantiate the worker with that. And so now we have the advantage of having a little bit more control over the worker in case we want to change it or something like that. And then also we avoid an HTTP round trip. So from a network layer, we're a little bit more optimized as well. So this is just kind of a cool example of where you can go with workers combined with the file API. Some places where you might want to use workers: text formatting of a long document, syntax highlighting, maybe not, depends on your use case. Image, if you're doing heavy image processing or dealing with large arrays. Also the audio API, for instance, the WebKit Web Audio API or the Mozilla Audio Data API. Depending on kind of the analysis that you're running, a worker might make sense. Also, the file system API, which is available in Chrome, has had support for workers for a while now. And this is really good. You might be dealing with large binary data, and you don't want that holding up the UI thread at all. You want to just let that happen as it does. And so letting web workers handle the interaction with the file system is the right way to go there. Cool. I want to touch on JSPerf real quick. Yeah, this is real cool. So JSPerf, if you don't know, is a site for performance tests. And so we have a few things going on here. We have a nice human-readable URL. And oftentimes, with a URL like join concat, this is now the definitive join versus concat string concatenation test. And there's revisions as well. So within the page, we have our variations of the code that we want to test. So this is the age-old concatenation with plus equals, or array join, which is faster. And I believe it's IE6 and 7 are faster with array join, and absolutely everyone else is faster with straight up concatenation, augmenting the string. So don't use array join anymore. But the nice thing here is that we can run the test and get our results and figure out kind of what it is. And so the site's used by a lot of people. In fact, jQuery's been using it for the library development recently. So let's say there's a few different variations of DOM traversal. The nice thing here is that we can do our tests with a few variations, kind of see what's going on, and then the results get reported to Browser Scope, which kind of handles what user agent it's coming from, what are the numbers, and kind of give us a really comprehensive table of what the story is across all browsers and where is each thing faster. And so, I'm running it here. This is WebKit Nightly, and we see, well, in this case, we have these traversal, and we have some different results. Yeah. So Jasper is really good. I like it a lot because it's kind of like the clearinghouse of performance best practices. People will say, oh well, you should use triple equals instead of double equals because it's faster. And now we can actually find out, hey, are they right, and are they right across all browsers or not? It's powered by Benchmark.js, which is a very finely tuned and calibrated benchmarking script that works not only in the browser but in Node and Narwhal and Ringo and all these different environments, and is definitely the right way to be benchmarking different variations of code. So a quick touch on the HTML5 boilerplate is a project that I work with, and recently we put out a build tool. The build script is just an Ant script, but the cool thing is that when you use it alongside one of the web server configurations, like for Apache or Nginx, you're basically going to get a 90% on your score for Google PageSpeed or YSlow. There's all these things that you've heard and you're supposed to be doing, like combining and minifying your JavaScript, your CSS, your image optimization, and the script does all these things. It also does HTML minification. It revs your file names so that we can cache bust when there's a new version, and then we upgrade the web server configuration to use far future expires headers because now we can, we have unique file names. So it does all these things for you, and we can basically take what was a C and B grade website and bring it up to some much higher scores. So I definitely recommend you dig into that if you'd like to not have to repeat all these performance optimizations every time you make a site, and let a script handle it for you. All right, I guess that's it for me. If you have any questions, you can leave a comment or hit me up on Twitter. I'd also recommend to check out html5rocks.com. We have a lot of tutorials on there of really good stuff, and we have a lot that are focused on performance and a lot of the things that I've been talking about here. So plenty more to read and learn there. So I guess that's it. Thank you very much for watching.